Dear students, today we are going to discuss electric field at a point due to an electric dipole. Also, we will discuss torque experience by dipole when placed in a uniform electric field. Now let us first see what is an electric dipole. It is a pair of equal and opposite charges separated by a small distance. You can see this diagram. Plus q and minus q both are separated by a distance twice a. So this twice A is also called the size of the dipole. The strength of a dipole is represented by its dipole moment. Notation is P here. So P is equal to Q into twice A. So the vector notation you can see P is equal to Q into twice A. You can see the vector twice A here in this diagram. Direction of twice A you see. So from this expression you can conclude that the direction of dipole moment is from negative charge to positive charge. So dipole moment is a vector and its direction is from negative charge to positive charge. You can see the SI unit of dipole moment, it is coulomb meter. For charge it is coulomb and for distance it is meter. You can see examples of electric dipoles. I will provide you this material. You will read all this. Next is ideal or point dipole. We can say a dipole to be point or ideal when twice A tends to 0 and charge tends to infinity such that P is finite. So you got the expression for P as P is equal to Q into twice A. So it is the product of charge and the size of the dipole. So when size of the dipole tends to 0, if it is very small, and Q tends to infinity, then we can say the dipole as the ideal dipole. Next is electric field at an axial point of a dipole. So you can see this dipole and this is the axis of the dipole, and on that axis we are considering a point P here. You can see at which we are finding the electric field. Twice is the size of the dipole, O is the center of the dipole. Now this point P is at a distance smaller from the dipole, that means from the center of the dipole. Now as we are going to find electric field at point P due to the dipole, so we have to apply the principle of superposition. That means we will try to find electric field at P due to minus Q and electric field at P due to plus Q. Then we will find the resultant of both the electric field. For that you need to know the distance of minus Q from P and distance of plus Q from P. So you can see here in this diagram, distance of minus Q from the P is R plus A, because this part is A, and distance of plus Q from P is R minus A. Fine. Also you can see the direction of electric field at point P due to plus Q and minus Q. You see at point P, this is the direction of electric field due to plus Q. Notation is, you can see E suffix plus Q, E plus Q, and this is the direction of electric field at P due to minus Q, okay, negative charge. So it is E minus Q. You can see this. Now let us write the expressions for E plus Q and E minus Q. Electric field due to charge minus Q at point P is, you see this, E suffix minus Q is equal to minus Q by 4 pi epsilon naught R plus A square P cap towards left. So you can see the direction of E minus Q, it is towards left. So instead of writing this, you can write Q by 4 pi epsilon naught R plus A square inside bracket minus P cap. So you can put the minus sign here also. So minus P cap means it is opposite to the direction of dipole moment. Electric field is opposite to the direction of dipole moment, so you can put the minus sign here also. Next is, you can see electric field at point P due to the positive charge E plus Q is equal to Q by 4 by epsilon naught R minus A square P cap towards right. You can see the diagram, the direction of electric field due to plus Q, and then you can find the resultant E axial E plus Q plus E minus Q. It's a vector addition. So uh, you can get the result as E axial is equal to twice PR 1 by 4 pi epsilon naught R square minus A square whole square P cap. So you can introduce dipole moment here. Okay, so already we have introduced dipole moment P is equal to Q into twice A in this, and for R is very greater than A, we can neglect the higher power of A. So doing all this, you can get the final expression as E axial is equal to 1 by 4 by epsilon naught twice P by R cube P cap. That means direction of net electric field is along the direction of dipole moment towards right. You can see the diagram. You can do it in a different way also, like you can put E minus Q is equal to Q by 4 by epsilon naught R plus A square towards left. You may not give the notation, this notation P cap. Simply you will write E minus Q is equal to Q by 4 by epsilon naught R plus A square towards left, and then E plus Q is equal to Q by 4 by epsilon naught R minus A square towards right. Now as you are going to find the resultant of E plus Q and E minus Q, what you have to see first you have to see whose magnitude is more. So definitely if you see E minus Q and E plus Q, so magnitude of E plus Q is more than that of magnitude of E minus Q. So how to get the resultant electric field? It is E plus Q minus E minus Q. E plus Q minus E minus Q. Magnitude of E plus Q minus magnitude of E minus Q, and the net direction will be along the direction of greater electric field. So you will get the same result. So E axial is equal to 1 by 4 by epsilon naught twice P by R cube P cap. Finally you can write. So you can see here that E is proportional to 1 by R cube. So it is 1 by R cube variation. Next is electric field at an equatorial point. Electric field at an equatorial point, you can see. Now this is the equatorial line. This is the equatorial line. You can see this. You have to consider this point P here on this equatorial line. Fine. So O is the center of the dipole. Now at point P, you have to draw electric field vector due to minus Q and plus Q. You can see this is E minus Q electric field vector at point P due to minus Q. You can see this E minus Q. Similarly, electric field at point P due to plus Q, it is like this E plus Q. This is negative, so it has to come like this. This is positive, so from this positive charge it has to go like this. Now you can see the length of E plus Q is equal to length of E minus Q, because magnitude of electric field at point P due to minus Q is equal to magnitude of electric field at point P due to plus Q, because these two charges are of equal magnitude, and this distance AP is equal to BP. Fine. So you got these two vectors E plus Q and E minus Q. So to get the resultant, you have to complete the parallelogram, and by drawing the diagonal, you can see that this is the resultant of these two vectors. Now if this angle is theta, then this angle is also theta, and as this angle is also theta, so this angle is also theta. You can see this. Fine. So you can draw the rectangular component of E plus Q and E minus Q. Now if you want to draw rectangular component of E plus Q, you can draw this. This is E plus Q sine theta. Fine, this is E plus Q sine theta, and this is E plus Q cos theta. Clear? Similarly, let us draw the rectangular components for E minus Q. So for E minus Q, this is E minus Q sine theta, E minus Q sine theta, and this is E minus Q cos theta. So E minus Q cos theta and E plus Q cos theta both are acting in this direction, you can see. Also you can see that E plus Q sine theta, E plus Q sine theta and E minus Q sine theta both are acting in the opposite directions. Okay, also magnitude of E plus Q is equal to magnitude of E minus Q. So E plus Q sine theta cancels out E minus Q sine theta. E plus Q sine theta cancels out E minus Q sine theta. So what remains? Only this remains. This is the resultant of E plus Q and E minus Q. So let us see how to go about this. E plus Q is equal to 1 by 4 pi epsilon naught Q by R square directed along BP. R, you can see what is this distance R. You have to apply the Pythagoras theorem. This is the distance R. So this is R square plus A square to the power half, or root over R square plus A square. So you can see here that E plus Q is equal to this directed along BP. You can see the diagram. E minus Q directed along PA, then E minus Q plus Q is equal to this, using the notation for electric field at a point due to a point charge, 1 by 4 by epsilon naught Q by R square formula we have used. So you can see net field E equatorial is equal to E minus Q cos theta plus E plus Q cos theta P cap. This minus sign is appearing because the direction of the resultant electric field is opposite to the direction of dipole moment. Have a look. So you can see this diagram. This is the net direction of electric field, resultant electric field. So this direction is exactly opposite to the direction of dipole moment. You can see dipole moment, it is towards right, and net direction of electric field is towards left. So that is why in that final expression that minus sign is coming. You can see this minus this, or you can put the minus sign here also inside bracket, P cap minus P cap you can put also inside bracket, that will also do, or you can put it here also. But as you have already learned that magnitude of E plus Q is equal to magnitude of E minus Q, so I can write like this, minus twice E minus Q cos theta P cap. Put the value of cos theta is equal to B by H. You can see this diagram again. Cos theta is equal to B by H cos theta. B means this, for this right angle triangle, B means A, and H means root over R square plus A square. So you can put the value of cos theta there. This is cos theta. So you put this, again introduce P is equal to twice QA, dipole moment, and also you introduce this. If R is very greater than A, already we discussed, you can neglect the higher power of A. So finally you can get this expression, E equatorial is equal to minus 1 by 4 by epsilon naught P by R cube P cap. So you can see here also that the electric field is inversely proportional to R cube, which is similar to the previous case. In axial point also we got electric field is inversely proportional to R cube. The only difference is, you see, E axial, it is 1 by 4 pi epsilon naught twice P by R cube, and here E equatorial 1 by epsilon 4 by epsilon naught P by r cube. That is the only difference. So we can conclude that E axial is equal to twice E equatorial. Okay, E axial is equal to twice E equatorial. So this is the relationship between electric field due to an electric dipole at an axial point and at an equatorial point. Next is torque on a dipole in a uniform electric field. So see this diagram. These parallel lines you can see represents uniform electric field equidistance lines. Okay, these are parallel line. This dipole is placed here in this electric field. Now you can see this positive charge of the dipole experiences a force QE along the direction of electric field, and this negative charge experiences a force QE opposite to the direction of electric field, because already we discussed that a positive charge experiences force along the direction of electric field and a negative charge experiences force along the opposite direction of electric field. But this force, you see, this magnitude of this force is equal to magnitude of this force, that is QE. So that is why net force experienced by the dipole is equal to 0. So you can see F total is equal to QE minus QE is equal to 0. But what is the amount of torque experience? For that you have to find the perpendicular distance between these two force lines. This is one force line, you can see, and this is the other. Class 11 already you have learned how to calculate torque. It is either force multiplied by perpendicular distance. Now here force is QE, but what is the perpendicular distance here? Perpendicular distance is twice a sine theta. So how can you get twice a sine theta? See, this angle is theta. This theta is the angle made by the dipole with the electric field, with the direction of electric field. So if you find sine theta here, sine theta is equal to P by H. So P is twice a sine theta, sorry, P is this, H means twice a. Fine. So sine theta is equal to P by H. Sine theta is equal to P by H. So that will give you this length is equal to twice a sine theta. So immediately you can calculate the torque. You can see here torque is equal to either force multiplied by perpendicular distance. So QE into twice a sine theta. So introduce P here, dipole moment, tau is equal to PE sine theta. So you can use the concept of vector product or cross product. Tau is equal to P cross E. This is the expression for torque experienced by an electric dipole when placed in a uniform electric field. Thank you very much.